Hi friends, let's have a look at problem 2507, smallest value after replacing with sum of prime factors. In this video, we're going to share a utility function to decompose an integer into its prime factors in the sense of multiplication. So first, let's look at the problem here. The statement is very simple. So we are given a positive integer n. So we want to replace n with the sum of its prime factors, and we would like to find the smallest value n will take on after these operations. So here are two examples. So in example 1, so we have 15. So if we decompose 15, we are going to have 3 times 5, because 3 and 5 are the corresponding prime factors. Then 3 plus 5 is 8, right? So then we decompose 8. So 8 is 2 to the power 3. So we have 3 factors 2. So the sum of these 3 2's is 6. So then we decompose 6 again. So we get 2 times 3, right? So the sum of 2 and 3 is 5. Then 5 itself is a prime number, so we cannot further decompose. So this is the smallest value n will take on. So example 2 is very special because n is a prime, so we return n itself. So the constraints or additional assumptions for this problem, and here is only one item, so that is the n is bounded below by 2. Notice that 2 is the smallest positive prime number, right? So 10 to the power 5 is the upper bound for n here. So with that said, we are ready to look at the analysis. So here we're going to give a treatment based on prime decomposition. So here actually the math behind is the fundamental theorem of arithmetic. So basically it says that an integer can be decomposed to be the product of a series of prime factors. So this decomposition is unique in modulo order, right, or permutation. So with that said, here the question reduces to the task of decomposing an integer into product of primes. So thus we could do this. Actually, to get the desired value is just a while loop. So in this video, our focus will be on writing a utility function to do the prime factorization. So here, to give you a feeling, so let's first get a sense. So we have 15, so its prime decomposition, we're going to get a list, consider 3 and 5. And for 24, we're going to get 3 2's and 1 3. So similarly for the last one, we're going to get this 3 2's and 2 3's and a 7, right? So this lists are the corresponding prime factors for the number given. So this format actually is nothing but the prime factorization. So with that said, we are ready to move forward to our coding session. So for the coding section, so first I'm going to write a utility function to get the prime factor for a given integer. So this is the so-called prime decomposition step. And then we can get the value of n in this problem by a for loop or by a while loop, to be more precise. So here, step 1, so a prime factorization. So factorization. So this is the main part. Actually, this function itself is very useful. So for that, let me use this one, get prime factors. So we accept a number, right? So and then what we are going to do, first I'm going to prime factors. So I'm going to initialize a list. So we're going to return the final state of this list. And then what we're going to do is to first I'm going to filter out all the factors of 2, right? So this is actually a while loop, very simple. So while number modulo 2 equals 0, right? So if this is the case, so we are going to do prime factors. So we can append this one by 2. then the number is divided by 2. This is the integer division, right? So after this while loop, so basically the number will be even. So let me write maybe here some annotation. So get all get all truths, right? So this is the one. So next, what we are going to do, we are going to get the larger prime factors. So get larger prime factors. So for this, actually we can use a while loop. So for I in range, so we can start from 3 because we have factored out all the factors, all the truths, and then we can end at the number to the power 0.5. That is square root. So we can make it integer, right? So to be safe, I have +1 here. So the step will be 2 because we don't need to consider even numbers. This loop, so we are going to do each factor, even odd factors, if they were prime, so we are just filter out that. So what we are going to do is if number modulo I equals 0, and then we're going to do prime factors append I, right? And then the number is divided by I. So this is the one major loop. So notice that we will not have this situation. So we will not modulo none, because for example here we have a none here, this one. But you know, because none is the square of 3, so we have modulo 3, so there's no nines. So this basically explains the soundness of this method. So don't forget that if number is greater than 2 afterwards, then this number itself, the current state, must be a prime. So we're going to prime factors append number. So this is the main code for our utility function. So here we can return prime factors. So this will give us the corresponding list here. But what we are interested in actually in this problem itself is the sum of the prime factors. So here actually we can return the sum also. This is just for convenience. So we don't need to return this one in some strict sense. But you know, we want to use it as a utility function. You can do this return, or you can just return this one. Anyway, so this is the utility function. Next, let's see step 2, the problem logic. So actually in here we have already put incorporate certain problem logic, but here what we are going to do is just like we check the prime factor sum and then compare with n. If they are not the same, so we just continue the procedure. So this is the while loop. Well, so let's get prime factors. So here this is the n, right? So but you know, here if we use this return, so we are interested in the second one, so that is 1. So if this does not equal to n, so what we are going to do, we are going to retrieve above, right? We let n equal this one. Right? And then afterwards, so if we exit this while loop, so this 2 will be the same, right? And then this is what we require, so we return n. So this short piece of code actually forms a solution format to this problem. So before we make any comments, let's first do a check. Yeah, it passes example 1. So now let's also examine a special case, that is we get a prime itself. So we will get 5 itself, right? So now let's look at the generic case. Yeah, it passes all the generic cases fast. So here let me maybe print something just in the case. So print get prime factors. So we can try several numbers. Let's try, say, 24 here. So we get 2, 2, 2, and 3. We get 2, 2, 2, and 3. And now let's also try 504. 504. So what do we get? Yeah, we get 3 2s and 2 3s and 7, and their sum is 19. So for the use of utility function, so basically you can just do this return, ignore this part. But that's a very small detail. So with that said, I guess that's about it for this specific problem. Thank you.